Welcome to the Corrective Corrosion channel. My name is احتشام زاده. I'm a researcher in the field of corrosion and protection of materials. Chapter 1, Section 4, Basics of Electrochemical Corrosion, Corrosion Circuits. Here is the reference of this video. 4 bases of corrosion process. 4 bases are observed in all cases of corrosion. 1 cathode, 2 anode, 3 path for ion transfer, 4 path for electron transfer. Here is the anodic reaction site that corrosion or oxidation occurs on it. Here is cathodic reaction site that reduction occurs on it. The direction of current is taken to be opposite to that of the flow of electrons due to the established convention that current is in the direction of the flow of positive charges. The oxidizing substances force the metal to provide electrons for reduction. The electrons are picked up at a cathodic reaction site. The areas over which the anodic and cathodic reactions occur individually vary greatly and may extend from positions a few atom distances apart on the surfaces to microscopic areas and even to macroscopic areas extending to hundreds of square meters. Summary of processes, terminology, and variables associated in wet corrosion. Anode, area AA, reactions, oxidation. General reaction, M produces Mn plus M electrons. Reduced state converts to oxidized state. Example, Fe produces Fe2 plus 2 electrons. Cathode, area, AC, reaction, reduction. General reaction, Xx plus X electrons produces X. Oxidized state converts to reduced state. Examples in deaerated medium. If acidic, 2H plus 2 electrons produces hydrogen gas. If neutral or alkaline, water is reduced and hydrogen gas and hydroxyl anions are produced. Continuation of the previous slide. Cathode. Examples in aerated medium. In addition to above, if acidic, oxygen is reduced in acidic solution and water is produced. If neutral or alkaline, oxygen is reduced and hydroxyl anions are produced. Aqueous phase variables. H plus concentration that is shown with CH plus and AH plus that are concentration and activity of H plus, and pH or minus logarithm of AH plus. The product of AH plus and AOH minus equals 10 to the power of minus 14. Dissolved gases H2 that is shown with CH2 or pH2. Concentration of hydrogen gas or the pressure of hydrogen gas. Oxygen that is shown with CO2 or PO2. Other dissolved species: ferrous cation, chloride anion, sulfate anion, ferric cation. Aqueous corrosion is most readily understood in terms of a dead shorted battery or an electrochemical cell consisting of 2 half cells. The solution or electrolyte above the corroding metal is the battery fluid, and the metallic path between the anodic site and the cathodic site is the external circuit. E is the symbol of general case of potential. E prime is the symbol of potential in the case of no current passing. E double prime is the symbol of potential when the corrosion current passes the interface. The elementary electrochemical corrosion circuit. At the anodic site, the net oxidation reaction is M produces Mn plus M electrons, and at the cathodic site, the net reduction reaction is X plus X electrons produces X. As a consequence of the transfer of ions and electrons at each interface, differences in electrical potential delta Va and delta Vc develop between the metal and the solution at the anodic and cathodic site respectively, where delta Va equals Vma minus Vsa, delta Vc equals Vmc minus Vsc, delta Va and delta Vc. The subscripts A and C designate the anodic and cathodic sites, and the subscripts M and S designate the metal and solution phase. These differences in potential, coupled as shown, constitute the electrochemical cell in which electrons are caused to flow from the anodic to the cathodic site in metal. As it was mentioned before, conventional electrical current flows in the opposite direction of electron flow. If the potential of the standard reference electrode is taken as 0, then for the general case, delta Va equals Vma minus Vsa. That gives delta Va equals Em, and delta Vc equals Vmc minus Vsc. That gives delta Vc equals Ex. The driving potential for the current in the solution is delta Vs equals Vsa minus Vsc equals Vma minus delta Va minus Vmc minus delta Vc. If it is assumed that the metal path is a good conductor, as it is, then the potential difference in the metal will be small. Thus, Vma is almost equal to Vmc. Then, the driving potential for the current in the solution using the recent equation is delta Vs equals Vma minus delta Va minus Vmc minus delta Vc. Delta Vs equals delta Vc minus delta Va equals E double prime x minus E double prime m. Delta Va and delta Vc. Delta Va relates to E double prime m and delta Vc relates to E double prime x. Corrosion current and current density in corrosion circuits. E double primes are double primed to emphasize their values associated with the corrosion current. Ohm's law results in I core equals E double prime x minus E double prime m divided by sum of Rs and Rm. Rs and Rm are the resistance of the solution and metal paths of the current. If high resistance films form, the total circuit resistance Rs plus Rm plus R interface increases and the corrosion rate decreases. If the current is uniformly distributed over the area of anode and cathode, then the current densities are calculated as IC equals IC divided by AC, IA equals IA divided by AA. Why is current density more important than current? Through Faraday's law, the anodic current density IA relates directly to corrosion intensity as mass loss per unit time per unit area, or to corrosion penetration rate as a linear dimension loss, thickness loss, per unit time. Faraday's law expressions: corrosion intensity in terms of gram per square meters per year and corrosion intensity in terms of milligram per square centimeter per year. Corrosion penetration rate CPR in terms of micrometer per year, millimeter per year, and milli-inch per year. I core is corrosion current density in ampere per square centimeter. Rho is density of the metal in terms of gram per cubic centimeter. AA is anode area in square centimeter. M is atomic mass of the metal in terms of gram per mole. M is the number of electrons transferred. M divided by M is EE, electrochemical equivalent. The second reason is it is observed that interface potentials E are functions of current density EI of the following form. E is a function that is affected by the area. EXIC equals E prime x plus eta x, IC equals E prime x plus eta x times IC divided by AC, and EMIA equals E prime m plus eta m, IA equals E prime m plus eta m times IA divided by AA. In these expressions, AX and EM become the potentials E prime x and E prime m if the current is zero. Therefore, relate to the potential differences across the individual interfaces at equilibrium, that is, no net transport of ions or electrons. These limiting potentials are referred to as equilibrium half-cell potentials, and when conditions of concentration and temperature are standardized, they characterize the standard equilibrium half-cell reactions. Overpotential in corrosion circuit. The above equations indicate that the existing potential with current flow is the equilibrium value plus a term that is called eta I, representing the shift in potential resulting from the current density. This shift is referred to as overpotential or overvoltage and increases in magnitude with increasing current density. During corrosion, IA equals IC, and this current is I core. Thus, Ohm's law can be written as I core equals E double prime x minus E double prime m divided by R total equals E prime x plus eta x times I core divided by AC minus E prime m plus eta m times I core divided by AA divided by R total. E double prime, the potential at the time of establishment of the corrosion current in the corrosion circuit. E double primes are the potentials when the cathodic and anodic reactions are coupled, when corrosion current passes the interface. The Ohm's law equation can be solved for the corrosion current. I core is a measure of the total loss of metal from the anode surface during corrosion. I core equals I core divided by AA. Thank you for your time. At the end of this video, challenge number 3. If you like to challenge yourself, please comment down below. If it is requested to measure the corrosion potential of an equipment that is exposed to a process solution, what potential does the electrometer high impedance voltmeter placed in the corrosion circuit show? E prime or E double prime? If you are interested in potential and its relative concept that requires use of reference electrodes, please don't miss the video entitled "Without reference electrode it is impossible", Chapter 1, Section 6.